Hi everyone, welcome back. Welcome, I guess, to the first lecture of this series, the first official lecture. So, in the previous one, we looked at in EM00, we looked at the prerequisites for Maxwell's equations and electromagnetics. And today we'll start with the actual electromagnetics part. Okay, hopefully you're excited about that. So, today we'll do Maxwell's equations. Okay, so we'll start with the point form of Maxwell's equations, which is curl of E, it's minus dB over dt. Curl of H is dd over dt plus j. And then we have the divergence of d equal to rho and divergence of b equal to 0, right? So this is nothing but Faraday's law. This is modified Ampere's law. And these are Gauss' laws of electricity and magnetism. So right off the bat, we can say a few things. We can see that these two are inhomogeneous Maxwell's equations because they have source terms, which is this and this, whereas these two are homogeneous because there are no sources, right? You don't see any sources here. And we have 6 different quantities here. We have E field, H field, B field, and D field. These are the unknowns. And then you have the J, which is, we'll describe what that is, but that's the current density, which is a known quantity, and rho is a known quantity. What I mean by that is that rho and J are essentially the sources of the fields. So these are usually given to you. And then you solve Maxwell's equations in different scenarios, which we'll do throughout the course, to find these fields. Okay? Which are given by E, P, H, and D. Okay. So what are E, H, D, and B? Let's label them or define them. E is called the electric field intensity measured in volts per meter. H is the magnetic field intensity, amperes per meter. D is electric flux density, and this is in coulombs per meter square. And B is the magnetic flux density, which is in Webers per meter square. And that's the same thing as a Tesla. Okay. J is what is known as the surface current density. And that's amperes per meter square, and we'll see what that is. And rho, which is the only scalar field, the rest of them are vector fields, is the volumetric charge density. We'll define rho and J more clearly. Shortly. Okay, so as I said, these 4 quantities are fields that we need to calculate, find given sources rho and J. Okay, will that good? Okay, so we gave these 4 Maxwell's equations, but in fact, J and rho are also related. And they're related by what is known as the continuity equation or conservation of charge, essentially. And it's a continuity equation which is equivalent to a charge conservation. And we can quickly derive that, in fact. So what we can do is we start with, let me actually do that here. This is dd over dt plus j. and I apply divergence on both sides. So when I take divergence on the left-hand side, this goes to 0 because divergence of coil is 0, right? And I apply divergence on this side as well. And what does that give me? That means d dt of the divergence of d is equal to minus of the divergence of j, right? We know that the divergence of d is nothing but rho, right? So we get that divergence of j is minus d rho over dt. And this is called it is a form of a continuity equation. And it is really a statement about conservation of charge. We'll interpret this a little bit more in a few minutes, but for now, this is another fundamental relationship. And it is actually very fundamental. Conservation of charge is one of the 4 fundamental conservation laws in physics, right? Okay, so there are essentially 5 relationships. You have Maxwell's relationship and you have conservation of charge as well. But we saw that we can derive conservation of charge from Maxwell's equations, right? So one thing I should say is that, this is a classical field theory, which means that we ignore the quantized nature of charges and currents. So we're kind of ignoring the fact that currents and charges are made of electrons. We just treat them as real variables, right? Or real or complex variables. Let's just say real for now. So essentially, rho is a real field, real scalar field, and J is a real vector field. Okay. And we'll develop electromagnetic theory based on that. For most of the experiments that we care about to develop in this class, most of the techniques we develop in this class, that's a good enough approximation. You don't really care about the quantized nature unless you're really dealing with phenomena where that's important, right? So it simplifies the development quite a lot. Okay, so let's actually define J and rho. So what are these things, right? So maybe we'll start with rho. It's a little simpler. So let's say I have some volume, some ball, which has some volume and some surface area. And I have some charge sitting inside it. Actually, let's say the volume is delta, which is a small volume, with a small charge delta Q sitting inside it. Okay. Then rho is defined as the limit as delta V goes to 0, delta Q over delta V, which is dq over dV in the limit. Okay, so as that volume becomes smaller and smaller, the amount of charge that's contained inside it converges to some value. Again, it only converges to some value because it's not quantized. Right? Keep that in mind. If it's quantized, then it doesn't converge as you make the volumes. Anyway, it doesn't converge. Forget about that. Just assume that if Q is continuous, continuously distributed in space, and it's a field, scalar field, as V becomes smaller and smaller, converges to this limit of dq over dV, right? And that's what rho is. It's the charge density, amount of charge per unit volume. Okay, that's simple enough. And okay, keep in mind that this is the net charge. It's not, I should mention this, that this is net charge, right? If I have positive and negative charges, then you have to kind of look at what the net charge is. That's important. Okay. Next is J. So how do you define J? So let's say I have some current that's flowing in space somewhere, right? What I can do is I can pick a point on this flow, and at that point, the flow is in some direction. Let's say it's along n hat, right? That's such a tangent to those flow curves, I guess, right? So that n hat has some direction, which means there's actually a unique surface, small unique patch of surface that has n hat as the normal, right? So n hat is normal only to one surface, right? If I change n hat, the surface also changes. Let me consider that surface, a small patch of that surface, which has an area of delta S. Or I guess I use delta A, but it doesn't matter. So now I can define J, which is the limit as this area goes to 0 of the amount of current flowing through that patch, right? Which is the charge per unit time flowing through that patch divided by delta A along n hat, okay, since it's a vector quantity. And this is nothing but dI over dA n hat, right? And that's what our J is. So it's the current flowing through a small unit of area in a given direction, which is the direction that is normal to that area. Okay, so that's the surface charge density. That's why it's ampere per meter square. Okay, so now from these two relationships, we can also find the total current, I. The total current I is integral. Total current I flowing through a large surface, S, is the integral over all these small currents, J, dotted with ds, because we care about the current that's flowing through the surface, right? Not flowing along the surface. And that's why you have to dot it with it, the ds, where this ds is what we wrote down here. It's nothing but, small del A, I guess. dA n hat, right? So that's small area times n hat. Okay, and we also have Q, which is the total charge, is the volume integral of rho dV. So these are directly a consequence of these definitions that we have here, right? This definition and this definition. Okay, so that's the total charge contained inside a volume. Is just the volume integral of the charge density per unit volume, right? That should be fairly straightforward to understand. Okay. Now, given this I and Q, we can actually also derive conservation of charge from here. So let's say I have some volume V with surface S, and I have some current flowing out of it. Like that. So this is my J. And I have some rho inside, right? Rho, which is the total charge inside. The total current flowing out is I. So it's a summation of all these current densities, right? So we can write I as what I wrote up here. I already have it here. But I is also equal to minus dq over dt. And the reason we have a minus sign there is that if q is increasing, charge has to be flowing in. But we drew the convention here as I going out, right? So that's why there's a minus sign. Okay, this is nothing but minus d dt of the volume integral of rho dV, right? And I can take this and I can say I is also nothing but volume integral, the divergence of J, EV, and that comes from the divergence theorem, right? So I have two relationships for I now. I can equate them, right? So I equate these two. Before I equate them, actually, there's one more step. So I can write this is equal to minus integral of the volume. Actually, it's getting a bit congested. So what I'm going to do is I'm going to move this derivative inside. And the reason I can do that is because I assume the volume is constant. ddt. Of rho. Okay. Okay, so now we have two integrals that are equal. What we would like to do is to say that their integrands are also equal. And we can say that here because this volume is arbitrary, right? So if I have two integrals and the volumes are arbitrary, they can be anything. and they have to be equal, then they have to be true for every point in that volume, because I can make that volume small and then equate different points, right? So arguments have to be equal since V is arbitrary. That's the argument. And from that, we can say that divergence of J is minus 0 over dt. So it seems like, we've kind of derived the law of conservation of charge just by some definitions of I and Q. Right here, there's no Maxwell's equation. So I just defined J and rho, and then I somehow derived conservation of charge. So the question now is this really a proof? Right? Is this a valid proof of conservation of charge? The answer to that is actually no, it's not. There is a step here that is not exactly rigorous. So I've kind of used a bit of a sleight of hand in this derivation. So I'm not going to tell you the answer here. You can think about it and put it in the comments below, and I'll let you know if it's correct. But this is actually not a valid proof. So in order to prove conservation of charge, you do need something called gauge invariance. So real proof, or vigorous proof, let me say, requires gauge invariance. Obviously, we already proved it from Maxwell's equations, but gauge invariance is a little bit more fundamental than that. We'll talk about gauge invariance and we'll derive it from Maxwell's equations, but it is actually a fundamental property of potentials. So we have to get to potentials, and then we'll talk about gauge invariance, and then you can use once you have gauge invariance, you will use Noether's theorem to prove conservation of charge. So, this theorem is a general theorem where you can prove different conservation laws from different invariant properties of nature, I guess. Okay, so I'm not going to go into too much here. It's not really relevant for this class, but I thought it's a nice, interesting aside that you can prove a fundamental relationship as fundamental as conservation of charge, or even conservation of momentum, linear momentum, angular momentum, energy. All of them come from invariant properties in nature. And Noether was the one who kind of developed that. It's really cool, actually. Okay, enough about that. Let's go back to our good old Maxwell and continue. So we derived Maxwell's equations, or not derived, we kind of postulated Maxwell's equations in point form or in differential form. Next, what we will do is we're going to actually, before we do that, let me actually show that they are in fact interdependent. They're not exactly necessary and sufficient condition to solve for the fields. They're just a sufficient condition. There is actually some interdependence built into Maxwell's equations. So let's quickly see that maybe. So we start with our Ampere's law. Right? Now you can take divergence on both sides. And when you take divergence both sides, left-hand side goes to 0, and the right-hand side becomes d dt, divergence of d, plus divergence of j. And the divergence of j is minus d dt of rho from continuity, which means that, again, you have the derivative of two terms that are equal. So you have d dt, divergence of d, equal to b dt rho, which means that divergence of d equal to rho plus some constant, right? So what is this constant? So if rho is 0, then the divergence has to be 0, because if the divergence is non-zero and it's some constant, there are many ways to kind of look at it. One way to look at it is to say that if the divergence is 0, it's constant everywhere in space without any sources, then d has to go to infinity as you go far away or go towards infinity in space, right? So the argument is that in a space where there are no charges and no currents, no sources, the fields have to be zero. So that's like the physics argument, right? Um, Sort of appeal to intuition or appeal to physics-based argument. So that's why the constant has to be zero. And that's maybe you're not satisfied with that. And if you're not satisfied with that, then maybe this proof is not the best for you. But I am kind of satisfied with that, okay, if there are no sources, then there cannot be any fields in an empty universe. And that's why that constant has to go to zero. So which means that divergence of D has to be zero. Okay, and we can do the same thing with the other Maxwell's equations. We have, this one's a bit easier. Right, you're taking in divergence on both sides, left-hand side goes to zero, and you're left with derivative of divergence of B is equal to zero, that's right. Which means the divergence of B is some constant. And once again, when there are no sources, you can't have any divergence. That's a constant. Otherwise, the B field blows up in space, right? So the only way that can be true is if that constant is zero. So then you get the other Maxwell's equations. So you can derive basically Gauss's law from equation of continuity and from the other two Maxwell's equations. Okay. Let's look at in integral form. Okay, so we have curl of H, once again, that's J, and that is your modified Ampere's law. We can take surface integral on both sides over some surface. Dot ds is equal to surface ddt plus j dot liquid ds, right? And then here I'm assuming that S is stationary. We'll revisit this in a few minutes, but assume S is stationary. So that means that I can take this derivative and pull it out, right? Yeah, let's do that. One more thing I can do is I can apply Stokes' theorem. So I'm going to apply Stokes' theorem here. So that gives me the contour integral of H dot dl is nothing but, so this integral is just the current, right? It's the surface integral of the current density, and that's nothing but I, which is a scalar quantity. Plus now I've taken the derivative out because that surface I'm assuming is stationary. Yeah, and this is your integral form of Ampere's law. Okay, I should say one thing here, which is that this is the correct, in some sense, the most accurate form of Maxwell's equations. Maxwell's equations are really macroscopic equations. So this thing that I did here, where I said S is stationary, and then I could pull this out, and that's how we ended up with this. The argument is actually the other way around. So you should actually start with this, because this is the fundamental relationship of Ampere's law. If you start with this and then say S is stationary, then you can pull this inside and then trace your steps back and end up with this point form of Maxwell's equations. This point form of Maxwell's equation that I wrote, the Faraday's law, the Ampere's law that I've written here, assumes that nothing is moving, that the surface is stationary. at the end of today's lecture, we'll actually see how to modify this, how this changes when in fact S is not stationary. So if S is not stationary, you can't pull this derivative inside as simply as that. And then there'll be another term in here which shows up. Okay, so I just wanted to keep that in the back of your head that we started with point form in a simpler form, which is the most widely used form of Maxwell's equations, which is this one. And we'll see at the end why that's the case. The added term is kind of very negligible when the velocities are very low. So this is still valid when you're not relativistic, right? But I just wanted to keep in mind that this relationship is in fact important. The more fundamental form, the form of modified Ampere's law. Okay, and similarly, we can do the same thing with Faraday's law, and you end up with integral E dot dl. B dot ds. So there's no current term now, right? Put this also in the next box. Okay. So let's do the other two as well. So we start with divergence of v equal to rho. We take volume integral on both sides. And that gives me, and then you apply divergence theorem. So that gives me surface integral of d dot ds over a closed surface is equal to q. And similarly, you can do the same thing with the divergence of b, which is 0. And that should give you the surface integral of b dot ds equal to 0. So these are your Gauss's laws. Okay. So these are the four fundamental Maxwell's equations, basically. And from here, we'll see what if you have a stationary surface, how do you deal with that, right? And we'll change the point form slightly because of that. Okay. So hopefully so far you're with me. I should also mention that we can derive KVL and KCL and a couple of other interesting relations from Maxwell's equations. So let's maybe quickly take a quick aside to do that, right? So I'll just mention it. We had divergence of J is d rho dt. Right? This is actually nothing but KCL, Kirchhoff's current law, right? Because, when we write KCL, what does it say? It says that the total current, let's say leaving a branch or a node in a circuit is equal to 0. Right? And there's an assumption under KCL, which is that charge cannot accumulate here. And if charge cannot accumulate, then that means that this term is 0, right? Which means that the divergence of J is 0, which is the same thing as this, right? This is a kind of a lumped model of this. So this is where KCL comes from. And then we also have KVL. So we just wrote down that integral E dot dl is minus d dt, the surface integral of B dot ds, right? So in electrostatics, this term is 0. And if that term is 0, then you end up with, contour integral of E dot dl is 0. And that's the same thing as KCL, right? Because in electrostatics, integral of along any curve, integral of E dot dl is actually a voltage. Right? It's not exactly the definition of voltage, it's the definition of EMF. But VEMF is equal to V in electrostatics. And we'll see that maybe later when we do potentials, but essentially in electrostatics, curl of E is 0, so it's a conservative field. So you only care about the endpoints, right? So this would be VB minus VA or phi minus VA for potentials. But you get this relationship which is that the voltage is defined as that. Excuse me. When I take a closed contour, it's the sum of all voltages along a closed contour, and that's zero. So in electrostatics, it's very trivial. But in quasi-statics, so in quasi-static regime, you need to be a bit more careful, right? So in quasi-static regime, what you can do, since you don't have zero here, the right-hand side is not zero. What we typically do in circuits is that we say that this is some voltage, right, which is nothing but ddt of current times inductance, right? So we essentially define inductance based on this. We assign a lumped inductor to account for lumped inductance to account for uh, this changing magnetic field. And of course, Li is equal to phi is how you define inductance, and this is nothing but your phi. This term is your magnetic flux. So to say that another way, you can essentially say that, okay, I have this term here, it's the derivative of the flux, and I can say flux is proportional to current, and the proportionality constant is the inductance, Li. So derivative of that, if I write it as a voltage, or it is in fact a voltage, then I can write that ddt of phi is V, which is equal to L di over dt, assuming L is not time varying. So then I can treat this whole thing on the right hand as another voltage, and then I take it to this side, and then I can say, okay, the total voltage around the loop is still zero, right? This has to be treated a little bit more carefully. You have to be careful on how you define the terminals and how the inductance is defined. But we'll treat it more carefully once we do potentials in a later lecture. So, okay, so essentially in electrostatics and quasi-statics, quasi-electrostatics or quasi-magnetostatics, you can still rely on KVL as long as you're a bit careful about how you define the inductors and so on and so forth, right? But of course, when the size of your circuit becomes very large compared to the wavelength, then you cannot rely on KVL and KCL. All bets are off, basically. So that's when you have propagation effects that you need to worry about. So when you do transmission lines and waveguides and antennas, which we'll do in this class, you can't use KVL and KCL anymore. So you have to go back to fundamental Maxwell's equations and do everything from there. Can't abstract away to circuits. Okay. So we derived KCL and we showed, okay, KVL is also from Maxwell's equations. One more relationship which we derive is Coulomb's law, which is also can be derived from Maxwell's equations. So let's do that. So we start with Gauss's law. Is equal to Q. And I say that, okay, if Q is symmetric, Q is symmetric, then D also must be symmetric. And I mean spherically symmetric here in terms of symmetric. So if Q is spherically symmetric, D also must be spherically symmetric, which means that D can only be some constant times R hat, right? Because on the surface of a sphere, R hat is the only unit vector that's symmetric or spherically symmetric. And the same goes for ds. It's a small patch on that sphere. It has to be ds times r hat. Cannot have any theta hat and phi hat components. Right? So hopefully that makes sense if you think about it. If you want a spherically symmetric solution, it has to lie on the surface of a sphere. And if it's lying on the surface of a sphere, then ds is r hat and d is also r hat. Okay, so then this becomes nothing but dr surface integral of ds. R hat dot r hat is just 1. So they kind of go away. And that's equal to q. And in the preliminary video, the previous video, the prerequisite video, we said that, okay, ds coefficient of r hat is r square sine theta d phi. on that, right? So we substitute this to this. And this surface integral is over the surface of the sphere, so you're only changing theta and phi, right? So this is dr r square, phi integrated from 0 to 2 pi, theta integrated from 0 to pi, sine theta, e theta, e phi. And this evaluates to 4 pi, okay? Which means that dr is q over 4 pi r square. And dr is nothing but epsilon naught er in free space. So if I write the electric field directly as a vector, that would be 4 pi epsilon naught r square r hat. And we haven't really established the relationship between D and E just yet. We'll do that in the next lecture. But if you've seen these quantities before, you know that in free space, at least D and E are related by epsilon naught, which is the permittivity of free space. Right? And that gives you Coulomb's law. Okay, so we've derived several relationships that are quote unquote basic from Maxwell's equation so far. Okay, so this is a good time to kind of treat the last part, which is what happens when you have moving surface boundaries. So earlier we said that, okay, there's this fundamental form of Maxwell's equations, an integral form, which is this one. If we have a stationary surface, then we can take this derivative inside. Take this derivative inside, we end up with this, and then, okay, from that we can kind of come back to point form of Maxwell's equations. But what happens when you don't have that, right? When you don't have S being stationary, and that can happen, we'll see examples of it. For example, if you have a coil that's moving, physically moving with some velocity in a magnetic field, right? That generates some EMF in the coil. And to treat those cases, which is exactly how a generator works, right? You need to be careful and you need to derive Maxwell's equations more carefully. Okay, so let's do that next. So first we set up what the problem looks like, and it's important to kind of understand that part. So I have some arbitrary surface S time t, and at time S of t plus delta t, it becomes a new surface, okay? And you can think of it as if, as if this, so maybe actually let me try this. So I erase this. Let me capture this. So essentially, I'm saying that this surface is moving from this point to this point. Right? It's moving up and down, let's say, or not up and down, it's just making a small displacement in the surface, or a small evolution of the surface in time. So when it moves a little bit, it sweeps out a volume, right? So you can kind of see that. So after it is moved, it has evolved to this surface. And during that motion, it has swept out a volume, right? So that volume is essentially like some kind of a distorted cylinder, has some wall, has a bottom surface. That's the wall, and it has a top surface. Okay, so we take a patch on this wall, and we call that patch delta S. Of course, it has a vector associated with it, which is pointing out. And right now, the bottom surface has a vector that's, let's say, pointing, if it was pointing up, then even the top surface, any patch that I take on the bottom surface, to color code this, the bottom surface is black. So if I take a patch on the bottom surface, that has a normal pointing up. If I take a patch on the top surface, that also has a vector pointing up right now, right? Because we move the same surface up a little bit. Now I can label a couple of more things. I can label every point on this surface, let's say it's moving up with some velocity u, it's a vector, right? Then this length is nothing but u times delta t. So I'm talking about, let me actually expand that figure a little bit so that little patch out there, just like this. The velocity here is u, which means that this component here is dl vector. dl vector is u times delta t. It's a vector quantity, right? And I'll call this as dx vector. Yeah, let's just leave it as that. Actually, let me rephrase this because I have it written differently. So I'll call this as dl vector, and maybe we can call this as dx vector. Okay. Okay, so you have one vector here, which is the length of this side times that direction. And we have another vector here, which is the length of this side times that direction. Okay, which means that delta S, which is also a vector, keep in mind that this is a vector, it has a direction, it's an oriented surface, is nothing but dl cross dx, right? Because that surface is not rectangular, it can be a parallelogram. And the area of a parallelogram is different, given by the oriented area is given by the cross product of its two side lengths, right? So, and the reason that dl comes on the left is the right hand rule. So you want this oriented surface normal to be pointing out. So it's dl cross u delta t. So just keep this kind of in mind, okay? We should have maybe developed it a bit later, but I'm just developing the geometry first before I go into the equations. Okay, so the geometry is kind of established. Now we can do the math. So we start with contour integral E dot dl. So this is our Faraday's law, the general form, where the derivative is on the outside. B dot ds. And we'll make a definition. I'll call this as minus vi m tilde. Minus vi tilde rather. Okay, which means that, just to make it easier to carry around the notation, this is nothing but d dt of s of t, b of t dot ds. Both the field and the surface are functions of time now. Okay, so now we'll apply the definition of the derivative, which is that we have some small time delta t, where it has shifted, times the surface integral t plus delta t, b of t plus delta t dot ds, minus surface integral at s of t times b of t dot ds. Right, so I've just applied the definition of the derivative. Because you have two time-dependent terms, you have to kind of separate it into two quantities like that, right? It's just f of x plus delta x minus f of x over delta x in the limit. Okay, so now we'll take a Taylor series expansion. For small delta t, okay? It's approximately equal to b of t plus db over dt, b of t, sorry, times delta t. Plus there are also actually higher order terms here, right? Hot. And I'm kind of ignoring them here. You can actually account for them, but what would happen is that they would all go to zero, because when you take the limit, the delta t in this term goes away, but the delta t in this term, because you have a delta t square, it will only cancel with the denominator 1 over delta t. Only one of them will cancel, and you'll still have delta t terms left over in here. So in the limit, they will all go to 0. So that's why it's fair to ignore them when you take this limit. Okay, so I'm just going to kind of ignore it from now itself, but it doesn't make a difference. You can keep it if you like. Okay, so now that I have that expansion, Taylor series expansion, we can put it back into our equation. Actually, now that we have the higher order terms, this is just 0. It's exact. Right, so we go back. So vi tilde is limit delta t goes to 0, 1 over delta t times that s of t plus delta t b of t plus db of t dt times delta t dotted with ds minus the other term b of t dot ds. Okay, so we need to kind of handle this integral. So let's do that. So I'll define another term, which I'm calling as VIT. It's defined as the limit as delta t goes to 0, 1 over delta t, t plus delta t, dv of t over dt, delta t dot ds. So what is this? So I've just taken this term and I'm treating that separately. And we want to see what this integral evaluates to. Okay. Okay. So this delta t term that we have here is a constant, right? Delta t is actually a constant because we make a small shift in delta t and it's fixed, right? Which means if it's fixed, then I can pull it out because we're not exactly integrating over delta t, we're integrating over the surface. So it's constant with respect to this integral. So I can pull it out and then cancel it with this. So this one cancels this, and then you can take the limit because then you don't end up with any infinities, right? So that gives me nothing but s of t, right? Because once you take the limit after canceling that term, this goes away. So yeah, s of t dp over dt dot ds. Right, so this is actually one relationship. So VIT will call what it is. It's the transformer induction voltage. But for now, let's just say it's VIT. So the other term left over is VIM, let's say, and we'll say what M is what is left over, right? You have limit delta t goes to 0, 1 over delta t times the surface integral at s of t plus delta t, b of t dot ds minus surface integral at s of t, the same thing, b of t dot ds. Right, so these are which terms? So these are the remaining terms, which is this term and this term. Okay. All right, so this is where the subtlety of the argument is. It's important to kind of understand this. But what is this? Right, so this is that top surface. I should draw that again. So this is our s of t plus delta t. And this is the bottom surface, right? It's s of t. So you're doing one integral over the top surface and one integral over the bottom surface of the field, right? Okay. Now, earlier we said, remember that the normal on the top surface is going up. The normal on the bottom surface is also going up. So what we can do is we can change the orientation of the bottom surface normal to face the other way. And when we do that, this ds now changes direction, right? Which means that this becomes a plus. Okay, so yeah, I'll say that this is our ds on the bottom surface, and this is the ds on the top surface, right? It's a small patch on those surfaces. Okay, if I do that, what I can, now you have a sum of two integrals, right? You have the sum of the top surface integral and the sum of the bottom surface integral. And I said that these two surfaces bound a volume, right? So you have a volume that's bounded by these two surfaces. If I take the surface integral over the whole volume, let's call that S naught, right? That is nothing but integral over the top surface plus the integral over the bottom surface plus the integral of the wall, right? That's the integral of the whole surface. So note that now all these integrals of all the surfaces have the normal components facing out, right? So these two are nothing but these two, right? So I can write that integral as, actually zoom out a little bit. So I can write VIM as limit delta t goes to 0, 1 over delta t of the integral over the entire surface of b of d dot t dot ds minus the integral over just the wall. Right, so if I take the entire surface and I remove the wall contribution, that just gives me the entire surface on the top and the bottom. Okay, so keep in mind that this b of t is the value of b on the bottom surface as a function of time and space, right? As a function of space, really, it's not, you're not doing integral, this is kind of a tricky integral. So you're not integrating b on the top surface with the top surface and b on the bottom surface with patches on the bottom surface. It's the same b for both integrals. So you have b fixed on the bottom surface and you're integrating over this entire top surface and bottom surface. And you can kind of see that the total surface minus the walls should give you what we had earlier. And that's the basic argument. So this is actually a closed surface integral, right? Because it's the entire surface. Okay, so if you can kind of see that, then basically we're kind of done. Okay, because this term goes to 0 from Gauss's law, because of course, closed surface integral over b dot ds is 0. It's easy to see that. You can just apply divergence theorem, and then the divergence of b is 0, right? So that's where that comes from. So we are left with nothing but limit delta t goes to 0, 1 over delta t of this other integral, right, which is double integral over the wall b of t dot ds. And we defined ds on the wall earlier, right? When we set up the geometry, we said ds, it's this one, it's dl cross u delta t, right? dl cross u times delta t. And that delta t should make you very happy because, okay, you can kind of move it out now, right? You bring it out, and you can cancel it. Because once again, delta t is a constant with respect to this wall integral. Then take the limit. So once you cancel the delta t and take the limit, the wall collapses into a contour, right? So this side wall, as you take the limit delta t goes to 0, becomes smaller and smaller and smaller, and ends up with 0 height eventually. And a wall with 0 height is nothing but a contour, right? So this becomes a contour integral of b dot dl crossed with u. Okay, And we can rearrange the terms using vector identities as u cross b dotted with dl. This is our VIM, right? So we can put VIM and VIT together, write the full relationship. So into V dot VL is equal to surface integral dv over dt ds plus integral over the contour u cross b dotted with dl. Okay, so this is called transformer induction voltage, and this is called motional induction voltage. Okay, and it's called motional inductance because there's motion involved, right? There's this U term in here. Okay, so one thing to kind of, it's interesting to see that all we did is that we just took this derivative which was out here inside. Pulling that derivative in when the surface is changing gives us a second term, which is the motional induction voltage, right? So that's the kind of the consequence of taking that derivative in. So this is really, it's the same thing as the Faraday's law we had earlier, except that now the derivative is inside, so we've pulled out a term. Both are the same. It's just easier to deal with this because, finding the entire derivative and then take entire integral and then taking derivative can computationally be harder sometimes than, let's say, finding the derivative and then taking the surface integral, right? So then you get this extra term out there that can be useful. Okay, so we can do the same kind of derivation for modified Ampere's law. I'm not going to do it again, but I'll write down the final relationship. You get an I out because you take surface integral of J and that gives you your I. You get a similar term as transformer induction, which is dd over dt dot ds. You get another term, which is not showing up earlier because the divergence of B was 0. With the divergence of D u dot ds, right? And this is nothing but rho. And you get the same contour integral at the end. Integral over the contour, u cross d dot dl. Okay. The other two Maxwell's equations don't really change because they don't have any time derivatives in them. So it's only these two that change when the surface is moving. So these are also called different things. So this is called the conduction current. This is the displacement current. This is drift current. And this is motional current. Okay. Okay, great. So we've kind of derived from the integral form of Maxwell's equations, what would happen if I have a changing surface. And it's kind of interesting to see actually there's a term in here which is u cross b, right? And it's contour integral of u cross b dot dl. On the left here, you have contour integral of E dot dl. So this makes sense that we can call this some kind of an electric field, right? And that is in fact the Lorentz field, right? From where you get the Lorentz force. So if you recall, Lorentz force is Q into V cross B or U cross B, right? And you can treat this as an electric field. That's really where this comes from. Is that start from here, you treat this as an electric field, and you say the force on this electric field due to this electric field on charge Q is Q into E, which is Q into U cross B. And that's known as the Lorentz force. Okay. So the last part is to see what happens to point form of Maxwell's equations when we use this quote unquote correct integral relationship where the d is already on the inside of the integral. The dt is inside of the integral, right? So let's do that. So we'll start with integral e dot dl. dv over dt dot ds plus contour integral u cross b dot dl. Okay. Okay. So I can take this contour integral to the left. I can write it as one thing. So I have contour integral of e minus u cross b dot dl, and that is equal to the surface integral dot ds. On the left hand side, I can apply Stokes' theorem. And that just gives me curl e minus u cross b dot bl is equal to dv over dt dot ds. Should be ds, right? So you have again two integrals and you want to equate them. They're equal to each other. And since s is arbitrary, it should be true at every point. Essentially, that's the argument, right? We use that argument before, which means in curl of E minus curl of U cross B is equal to minus dB over dt. So this is the point form of Maxwell's equations where you account for moving contours or moving surfaces. Okay. Okay, so we've added essentially this additional term, which came from the motion, right? The reason we usually don't care about it is that we'll see later that actually B in terms of just units is way, way smaller than E. And beyond that, if U is also very small compared to the speed of light, then this whole term becomes negligible. You're essentially just left with our original Maxwell's equations that we started with. So we'll just stick to that as we move forward in the course. Okay. So you can do the same thing with Ampere's law. You would get del cross U cross D is equal to dt over dt plus rho u plus j. So this is point form of Maxwell's equations with moving, with motion included. We have two extra terms now, this one and this one. Okay. All right. So it's also important to keep in mind that, cross products are not associative. So you have to take this cross product first and then apply curl. You can't do this first and then take a cross product, right? So that's an aside. Okay, so that concludes essentially what I wanted to discuss today with regards to Maxwell's equations. So just to summarize, we started with the differential form, point form, and then from there, let's go back. Yeah, started with point form, and we derived continuity equation, defined the current and charge densities. Then we showed that Maxwell's equations are interdependent. So it's not entirely necessary to have all of them. And from there, we use some vector calculus relations to derive the integral form of Maxwell's equations. We derive Coulomb's law, KVL and KCL. And then we said, okay, when I have a moving surface, what do the point form of Maxwell's equations look like? The differential form. And we derived those as well. And that was the ending. That was the last part of today's lecture. Okay, so hopefully that was interesting. In the beginning, it's a little bit more theoretical, and later on, we'll start developing more and more the practical side of electromagnetics. But it's very important to know these things, to kind of have in the back of your head, where all of this comes from, and really this demonstrates that Maxwell's equations are really fundamental, right? Because we can derive very fundamental relationships from them. So hopefully you found that interesting. If you have any questions, you can leave them in the comments below. If you're taking the class in person, of course, you can come and ask me anytime. Um, and there was one question that I asked. I asked, why that derivation of conservation of charge is not exactly valid. If you have the answer to that, post it in the comments below. If not, thank you so much. I will see you in the next video.